Hello and welcome to this video about eigenvector proofs. In this video we'll prove this theorem 5.2. I'll go through the statement of the proof slowly and gently before proving it. So we've got a linear transformation called L, and it's a function of an element in the vector space called V. The output of this function L is also in the same vector space V. We've got a set called F, and it contains vectors, which are a basis of vector space V, and these vectors are eigenvectors of L. We can say that L has eigenvectors because it's interchangeable with a matrix. It practically is one. So the theorem states that the matrix representation of L with respect to the set F will be a diagonal matrix, and the diagonal entries of this matrix will be the eigenvalues of L. So the matrix representation isn't a standard basis representation, but its basis is the set F. This equation needs some explanation. It's a way of calculating the entries of a matrix from the vector and its basis vectors, and it isn't very clear why it's true. A good place to start it is to compare it with the standard basis and the standard basis vectors. Here's the equivalent equation for the standard basis. So we'll expand out this sum into dot notation to make it easier to follow. I'll just scroll the screen up to make some more room. This is what the standard basis vectors look like when we substitute them in. They have a generalized number of elements, and so we need to add dots between the zeros. Then we can multiply the coefficients by the standard basis vectors to get these column vectors. We can then add all of these vectors together to get this column vector. This will place all of the coefficients in order in this vector like this. And this is equal to the column j of b. We can write it out as this function like this. It's easier to see that this equation works using the standard basis. So to get the equation we're going to use, we'll swap the standard basis vectors with the vectors f1 to fn that we're going to work with. I'll just scroll the screen up again to make some more room. This is the equation that we want to explain. We'll expand it out into dot notation. These coefficients represent a column of matrix A. We could write this out like this. So these basis vectors have a similar behavior to the standard basis vectors. We can use them to construct a matrix column by column using this formula. So now to get back to proving this theorem. And since these vectors are eigenvectors of L, we can write out these equations. L applied to each of these vectors is equal to a scalar multiplied by each of these vectors. The scalars are the eigenvalues corresponding to these eigenvectors. We'll call them lambda, being the standard variable to represent them. And we'll let A be this matrix representation of L with respect to the set F that contains all of these eigenvectors of L. And we can already define the entries of A to be little a with these subscripts. So I'll just scroll the screen upwards to make some more room. We can then write these eigenvector equations as this one eigenvector equation using a subscript k to stand for all of the numbers from 1 to n. Now we can use this equation that I've explained a bit before I started this proof. It can be used for any vector u that's in vector space V. We can then substitute one of the basis vectors fk in for u. Fk can stand for any of the basis vectors in set F. I'll just scroll the screen up again to make some more room. We can expand this sum out into dot notation so as to more easily follow it. Since lambda k is the eigenvalue corresponding to eigenvector fk, we can substitute it in for L. And now we can get this result for these coefficients of these vectors. All of these coefficients are 0 except for a double k, which is equal to the eigenvalue. So these coefficients represent a column vector with only one non-zero entry. And since matrix A is a matrix representation of L, then we can substitute it in for L like this. So I'll just scroll the screen up again. We can also say that L is diagonalizable because there are n eigenvectors in this set, enough to make a change of basis matrix. We can write the matrix A like this. Since it's made of columns with only one non-zero entry in them, A is thus a diagonal matrix, with the diagonal entries being equal to the eigenvalues. We have to properly align them with their corresponding eigenvectors. The delta function written inside the brackets shows that A is a diagonal matrix. We can draw A as a generalized matrix like this. We can even write A as a diagonal function like this. So A is the diagonal matrix that's a matrix representation of L with respect to the eigenvectors of L in set F. And the diagonal entries of A are the eigenvalues of L. So we've proven this theorem. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.